Artificial intelligence has transformed decision-making and optimization processes in the modern era. AI systems use algorithms to minimize computational resources and maximize solution quality. This project focuses on the implementation and comparative analysis of such algorithms for solving real-world problems. The algorithms used are divided into number one, uninformed search algorithms, which are breadth first search, BFS, and depth first search. And number two, uninformed search algorithms, which are A star search algorithm and greedy best first search algorithm. The project evaluates algorithm performance based on time complexity, space complexity, and path optimality.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ikhlas dan bin Muhammad Ashdi. Okay, now we continue to the problem description. And then the problem description is about the eight puzzle is a classic state space problem involving that providing 3 times 3 grids and 8 number tiles and 1 empty space. And the main objective of these issues is about the rearrange the scramble puzzle into the goal state. And the tiles are moved by sliding them into the empty space, and the valid movement is just up, down, left, and right. And the movement rules, the empty space must remain within the grid boundaries, and a move is a valid only when swapping with neighboring tiles. And the puzzle contents is about 362,880 possible configuration and a complex but finite search space. This project evaluates AI search algorithm based on time capacity, space complexity, and solution optimality. And the project also helped develop a practical implementation skill and analytical responsibilities.
Hello, Assalamualaikum. My name is Anik Basim bin Ramza and I will continue the presentation. I will present about the search problem formulation for this project. For the search problem formulation, in our implementation, we represent these puzzle stats as flattened tuples. For example, the goal state is stored as 1, 2, 3, 4, 5, 6, 7, 8, and 0. We choose tuple over list because tuples are immutable and hashable. This is a critical optimization, which is it allows our algorithm to store visited state in a set for near instant lookup, preventing the search from expanding the same configuration twice. The movement of tile is governed by four possible action, which is moving the blank space up, down, left, or right. In our specific initial state, the blank is in the center, giving us a branching factor of b equal to 4. While there are over 362,000 possible arrangements of this tile, it is important to note that only half, roughly 181,000 states, are actually reachable due to mathematical parity rules. Our code is designed to navigate this reachable state space. Finally, we apply a uniform path cost of 1 for every move made. This means that the total cost of a solution is simply the number of steps taken. By defining the problem this way, we enable algorithms like BFS and A search to mathematically identify the shortest, most optimal path to the solution.
Okay, for the implementation, we didn't just write one long script. We used a modular architecture to separate concerns. Our code is divided into three files, which are state.py for the puzzle logic, algorithm.py for the search strategies, and main.py to run the experiments. This makes the system easier to debug and more organized. Okay, now inside state.py, we define the state class. We choose to represent the board as a 1D tuple instead of a 2D list because tuples are immutable. This allows us to use them in a visited set for efficient lookups. Our movement logic uses the getNeighbor method, which converts the flat array into grid coordinates to ensure tiles only move within valid boundaries. Next, in algorithm.py, we implemented all four algorithms. For BFS, we use a first in, first out queue from the collections module to guarantee the shortest path. For DFS, we implemented a max depth or depth limit as a safety measure to prevent the program from crashing in the large state space. For our informed searches, a search and greedy, we utilize the heap queue library to always expand the node with the lowest cost first. Finally, our main.py serves as the evaluator. To ensure a fair comparison, every algorithm starts with the exact same scramble board. We optimize the execution using a visitor set to skip configurations we have already seen, which significantly speed up the search. The results you see in our tables were automatically generated by this script, tracking time, steps, and nodes expanded.
For the heuristic design, now let's look at the brain of our informed search, the heuristic function or HN. In artificial intelligence, a heuristic is an informed guess that estimates the cost from our current position to the goal. By using this, we prevent the algorithm from wasting time exploring unrelated paths, which significantly improve our search efficiency. For this project, we applied the Manhattan distance to guide both of our A search and greedy best first search algorithm. How Manhattan distance work? So, how does it work? Unlike the simple misplaced style count, Manhattan distance is much more precise. It calculates the total distance each tile must travel, horizontally and vertically, to reach its correct target. We exclude the blank space from this calculation. This approach is perfect for the 8 puzzle because our tiles are restricted to grid-based movement up, down, left, and right. By measuring exactly how far each tile is from its destination, the algorithm can prioritize moves that actually bring the board closer to the goal state. Finally, the most important property of Manhattan distance is that it's admissible. In AI theory, an admissible heuristic never overestimates the actual cost to reach the goal, because every move in an 8 puzzle shift a tile exactly closer to its target. Our estimate cost Hn is always less than or equal to the true cost H multiplied by n. This mathematical guarantee is why our A search algorithm is so effective. It doesn't just find any solution, it is guaranteed to find the optimal solution with the minimum number of steps.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ikram Mazuki and matrix number is 078194, and now I would like to present to you about complexity analysis. Complexity analysis is performed by determining the number of branching factors and the depth of the algorithm. The branching factor B represents the number of alternative motions of the blank space from any given state. The blank space can move 4 ways in the center, 3 in the edge, and 2 in the corner, resulting in an average branching factor of B equal to 3. Meanwhile, depth D is the length of the shortest path between the initial and target states. As you can see at the table, BFS has a time-space complexity of O round brackets B to the power of D, assuring path optimality by investigating every node at given depth before moving further. However, this results in an exponential memory development, making it unfeasible for complex puzzles. In comparisons, DFS is more memory efficient with a complexity of O round brackets B to the power of M, where M is the maximum depth. Nevertheless, its time complexity of O round brackets B to the power of M lack of optimality mean it may pursue unnecessarily long pathways before identifying the answer. Informed search algorithms such as A-search and greedy best first search seek to optimize these complications by using heuristic functions to direct the search process. The worst case time complexity for A search remains O round brackets B to the power of D. However, according to our findings, A search is the most effective algorithm since it combines the optimality of BFS with the speeds of heuristic-driven search. Using an admissible heuristic, A search expended significantly fewer nodes than BFS while maintaining the shortest path to the goal. While DFS required the least amount of memory, it frequently produced highly suboptimal path, making it unsuitable for puzzles requiring the shortest possible move sequences. And now I would like to present to you about optimization techniques. Several optimization techniques were implemented in this project to improve the efficiency and performance of the 8 puzzle solver. Since the puzzle problems contains a large number of possible states, the algorithm may repeatedly explore the same configurations, causing unnecessary computations and increased memory usage. To overcome this issue, a visited set or memorization technique was applied. For the first one, tuple-based state presentation. Instead of representing the puzzle as normal 2D list, each puzzle configuration is stored as flattened tuples such as open bracket 1, 2, 3, 4, 5, 6, 7, 8, and 0. Tuples are immutable and hashable, making them more efficient for storage comparison inside visited sets. In addition, the breadth first search BFS algorithm uses Python's data structure to optimize queue operations. The DAG structure allows insertion of and removal of nodes in constant time of O open brackets 1. which significantly improve performance compared to using a standard list structure. Second one is hash-based set. Every explored state is stored inside a hash-based set, allowing the algorithm to quickly check whether a state has been visited before expanding it again. This optimization helps reduce duplicated search, prevent infinite loops, and improve the overall execution of speed of the algorithm. And for the first one is Manhattan distance heuristic. For informed search algorithms such as greedy-based first search and A search, the Manhattan distance heuristic was used as an optimization strategy to guide the search process more intelligently. Instead of exploring every possible state blindly, the heuristic estimates the distance between the current state and the goal state based on the position of tiles. This allows the algorithm to prioritize more promising states and reduce unnecessary node expansions.
Okay, now I will continue about the result comparison. A standardized initial state it start from 1 to 4 for the first line, 305 to second line, and 768 for the last line. And it was tested to reach the initial the goal state. Is the goal state is the number from 1 to 8, and the last one is the empty space. In order to evaluate the performance of each algorithm, in this problem, the integer 0 represent the blank space and act as the only movable position that allows neighboring ties to slide in the up, down, left, or right. And the algorithm also will compare based on four main criteria, which are nodes expanded, time taken, memory usage, and path optimality. Okay, now we see about the what the result in the table based on four algorithm. Is it the BFS, DFS, greedy, and A star search? We start with the breadth first search, or we call it the BFS. The search type is uninformed and the highest memory usage. BFS also take time taken in the millisecond is about 1.302525, and the node expanded is 98,385, and the step for the path length is take about 22 step, and the path optimality is just moderate. And we continue to the depth first search, or DFS. The search type is same like BFS. Is it the uninformed, and the memory space is high, and time taken take for 1.12541, and the node expanded is about 86,896, and the path length is about 50 step, and the path optimality is no. And the greedy and A star search, a greedy is a informed search type, and its take a memory usage is lowest, and its time taken is about 0.001923, and the node expanded is 120, and the path length they just take 42 step, and the path opportunity is no like a DFS. And the last one is star search. Search type is informed, and memory usage is low, and time taken is 0.026306, and node expanded is about 1978, and the path length is a search is just take 22 step, and the path optimality is yes. This is our result comparison for the all algorithm that provided. That's all from me. Thank you.
In conclusion, different algorithms show different performances in computational efficiency, memory usage, and solution quality. The Manhattan distance heuristic played an important role in improving search efficiency. The project successfully achieved its objectives. Number one, implementing AI search algorithms, comparing algorithm performance, and performing complexity analysis. This project strengthened problem solving skills, analytical reasoning, and practical AI implementation knowledge. The knowledge gain provides a strong foundation for future AI and optimization challenges. And thank you.